Okay, good morning everyone. This is Wang Yiyang from Okoji Lab, and I'd like to introduce my research. The title is Distributed Multi-Agent Reinforcement Learning, Traffic Signal Control at Arterial Intersections, Considering Information Sharing. This study is based on the big progress made in reinforcement learning, or RL. RL is an optimal control concerned with how an intelligent agent should take actions in a dynamic environment in order to maximize the reward. The existing adaptive traffic signal control (ATSC) has limited flexibility while reacting to traffic and poor scalability in large-scale urban networks. Through RL, we believe that the ATSC can be more flexible. And from the right-hand side figure, we can see how the RL environment is abstracted to a traffic environment of an intersection and how it processes in such an environment. The state features is the real-time traffic state observed by the traffic detectors. They're inputted to the RL signal controller, which is the agent, and it takes actions, often the signal indicators, according to a policy. The environment being affected by the actions will change and generate the rewards, which is often the traffic indicators that we wanted to maximize or minimize, and together with the new traffic states. Based on the experience composed of states, actions, and rewards, the policy of the agent is updated according to a given learning methods and finally converges to optimum after cycling again and again. In order to improve the scalability challenge in a large-scale network, recent studies of RL-based ATSC focus on multi-agent RL, also MARL. It assigns one agent at one intersection and let the agents interact with each other. However, most of them assumes the agents to only focus on its own intersection, and we're afraid each section cannot coordinate well with each other. So we wonder if we can use the traffic states of agents' own intersection plus their adjacent intersections to facilitate the coordination. We call it the information sharing mechanism. We create a 3-intersection corridor on Sumo with lane area detectors and induction loop detectors at the end of each lane, which feed back real-time traffic data. We use least squares temporal difference as the learning method and with linear function approximators. The action is to decide the signal phase of the next action interval, and the reward is the total throughput of the intersection during the reward interval. For the state features, we will try the composition of 4 different traffic indicators to form the state features. Then we run 2 experiments. The first experiment A is to verify the effectiveness of information sharing. We selected different state feature compositions with and without information sharing. See the left-hand side figure, and the group 1 contains information sharing, which is the agent vehicle number for this example, and the group 2 doesn't. And after running the simulation, we found that agents with information sharing, group 1, usually provide lower waiting time and lower number of halts comparing to those without the group 2. So we can say that information sharing takes effect. For the second experiment, B, it is to figure out which state feature can make a difference among all compositions with information sharing. So after comparing various groups with information sharing, we found that groups with local vehicle number and adjacent elapsed green can better improve average waiting time and average number of halts in the arterial direction, especially in the main direction. So we hope that this finding can facilitate the progress of MARL-based ATSC and its final deployment in the real world. Thank you very much. That's all.